In this video guide, I want to cover a few more additional topics in the energy chapter. And another topic that comes up is the concept of efficiency. So for this very first problem, we got to find out which of the following definitions best represents efficiency. And efficiency is basically like the work output divided by the work input. So the best option here is going to be B. It matches the straight up definition right there. I would just say when we're doing efficiency problems, just make sure that we are aware of the different ways we can actually calculate work. All right, so we found so many different ways to find work, right? So work is equal to, force times distance. And we also know work is a form of energy. So there's different kinds of energies that we can get from the work energy theorem. So sometimes work was just equal to your potential energy. Sometimes work was equal to your kinetic energy, depending on what kind of scenario you were given. We also know that power equals to work divided by time. And if we manipulate this formula here, we know that work is equal to power times time, right? So basically, even though there's work output and work input for efficiency, just be aware that we've come up with different ways to calculate work, and we have to just be aware of that when we're trying to calculate efficiency here. So once we look at the next few problems, hopefully some of this will come together here. So in this first problem, we have a motor using 1,500 watts. Takes 52 seconds to raise a 250 kilogram load vertically, 24 meters, and we want to find the efficiency of this motor here. Okay, so based on the previous slide here, we know that efficiency is equal to the work output. I'll just say work out for short, and we divide that by the work in. All right, so we got to figure out what the output is and what the work input is for these particular problems. Okay, so for this very first problem, we know that, well, it's being raised, this motor is raising this 250 kilogram load vertically 24 meters, right? So that is that's the work out, all right? We're raising it 24 meters. And it takes 52 seconds and 1,500 watts to do this, so this is the work in. Okay, so the work out is simply going to be, actually let me just complete this on the next line here. The work out is simply going to be mgh, your potential energy, and then we're going to divide it by the work in. And since we know that watts is a form of power, power is equal to work divided by time. If we manipulate this formula here, we know that work is equal to power times time. So I'll put power times time on the denominator there. Okay, so let's go ahead and figure this out here. The mass in this particular problem is 250. The acceleration due to gravity is 9.80. And the height that we actually reach is going to be 24 meters. And then we can divide this by the power here, and the power that we're given is 1,500 watts and 52 seconds. So 1,500 watts and 52 seconds. Okay. Now, once we multiply the numerator and divide that by the denominator, let's just go ahead and multiply the numerator out. I get 58800, and we divide that by the denominator, which is 78. And then 3 zeros, so 1, 2, 3. And I want to mention that for these efficiency problems, the denominator should always be bigger than the numerator. All right, and once we have established that, we can just times this by 100 to get a percentage here, and the efficiency for this particular problem is 75%. All right, so the motor is 75% efficient. Here's another simple efficiency problem here. So in this problem, we have a 15 kilogram cement-filled bucket, and it's raised vertically to a height of 5 meters in 4.2 seconds, and the motor draws 373 watts of power. So we got to find the efficiency of this lifting system. Okay, so we know that efficiency is equal to your work out divided by your work in. All right, so this is actually very similar to the previous problem, right? So the work out is actually that we raised this particular 15 kilograms cement-filled bucket. We actually raised it to a height of 5 meters. So that is your work out. Okay, and since we're raising it a vertical distance, we know that's equal to the work here is going to be your potential energy. And since we're dealing with watts of power, we know that power is equal to work divided by time. So now we know that work is equal to power times time. So the denominator should be power times time. Okay, let's go ahead and plug in the numbers here. So potential energy is mgh. And my denominator will be power times the time. Okay, let's just continue. Actually, let's just continue vertically here. So the mass in this particular problem is going to be 15 kilograms. So 15 times 9.80, and the height here is going to be 5 meters, right? So 5 meters, and then we divide that by the power, which is 373 watts of power, and the time here is going to be 4.2 seconds. Okay, so if we go ahead and figure this out, I believe the numerator is roughly 735, and hopefully the denominator will be bigger, and it is. It's 1,566.6, and then we just kind of times this by 100. This will give us a percentage here, so this is roughly 46.9% efficient there. Okay, so efficiency is just a follow-up concept from some of the concepts that we have been building upon from work and power. I'm now going to move on to a random kind of concept problem here. So there's a word problem here, and we just need to kind of explain what the correct answer is using proper principles of physics. So in this word problem here, we have a cyclist that must do 1,000 joules of work to speed up from 0 meters per second to 5 meters per second. Okay, so if I go from 0 meters per second to 5 meters per second, we're stating that this requires 1,000 joules of work. Okay, now the same cyclist must do 3,000 joules of work to speed up from 5 meters per second to 10 meters per second. Okay, so that's going to require 3,000 joules of energy. And we assume that there's no friction in both cases, and using principles of physics, explain why more work must be done to speed up from 5 meters per second to 10 meters per second compared to 0 meters per second to 5 meters per second. Okay, and we simply just can't say because the problem tells us this requires 3,000 joules for this particular case, and 3,000 joules is much bigger than the first case, which is 1,000 joules. So we just can't say because 3,000 joules is bigger than 1,000 joules. Okay, so here's a nice little typed up answer here, and I'll just kind of read it out here. So when the cyclist speeds up from 0 meters per second to 5 meters per second, the initial kinetic energy is relatively low since the initial velocity is 0. Now, when we compare this to the cyclist who is already moving at 5 meters per second, therefore, all right, here's a random energy problem here, and it's a word problem where you need to kind of explain the proper solution. So for this problem, we have a cyclist who must do 1,000 joules of work to speed up from 0 meters per second to 5 meters per second. So when we're going from 0 meters per second to 5 meters per second, this requires 1,000 joules of work. Now, the same cyclist must do 3,000 joules of work to speed up from 5 meters per second to 10 meters per second. Okay, so this case down here, when we're going from 5 meters per second to 10 meters per second, that requires 3,000 joules of work. Now, we ignore friction in both cases, and using principles of physics, we need to explain why more work must be done to speed up from 5 meters per second to 10 meters per second. So it takes more work to go from 5 to 10 than 0 to 5 meters per second. And once again, we are told that friction plays no role in this problem. Now, we simply can't say that, since this requires 3,000 joules of energy and this requires 1,000 joules of energy, therefore going from 5 meters per second to 10 meters per second requires more work because 3,000 is bigger than 1,000 joules. That's not a proper answer. So here's a typed up explanation of what is an acceptable answer here. So when the cyclist speeds up from 0 to 5 meters per second, the initial kinetic energy is relatively low since the initial velocity is 0 compared to when the cyclist is already moving at 5 meters per second. Okay, so since we are starting at 0 meters per second, we're saying that there's low kinetic energy here. Okay, therefore there's less work required to increase the kinetic energy from 0 joules to 1000 joules. However, when the cyclist is already moving at 5 meters per second, the initial kinetic energy is higher compared to when starting from rest. So to achieve the same increase in kinetic energy from 1000 joules to 3000 joules, more work was required because we're initially starting at 5 meters per second, right? So this initial kinetic energy is higher, and so to achieve the same increase in kinetic energy, what that means is when we're going from 5 meters per second to 10 meters per second, we need more work. So in summary, more work must be done to speed up from 5 meters per second to 10 meters per second compared to going from 0 to 5 meters per second, because the kinetic energy of the cyclist is already higher at 5 meters per second, requiring more additional work to increase it further. All right, so that's a very good explanation for this particular problem here. Here's another good review question for the energy chapter. So we're given a graph, and the question states that starting from rest, our farmer pushed a cart 12 meters, and the graph shows the force F which he applied plotted against the distance D. Okay, so we have force on the y-axis, and we have the distance traveled on the x-axis. And the very first question is, we need to figure out how much work the farmer did to move the cart 12 meters. Okay, so we know work is essentially equal to force times the distance. And basically what we're doing for these graphing questions is that since the y-axis is measured in newtons, which is force, and since the x-axis is measured in meters, which represents distance, the work for this particular case is simply the area under the graph. Okay. If I take a look at this horizontal line here, and if I go straight down here, and if I look at this particular shape here, so what we're trying to say here is this area under the graph represents a rectangle. So here's your length, and there's your width, right? So I know this area is really length times the width, right? But the length is measured in newtons, and the width is measured in meters. So if I take, if I say length times width, in terms of the units, it's going to be newtons times meters, which equals to the work done, right? So therefore, in order to find the work for this particular problem, we need to calculate the area underneath the curve for these two regions right here. Okay, so if I want to find the work over here, length times width, I'll say length times width. So let's say we have 140 there, and we times it by the width, which is 7, so 140 times 7. Then over here from 7 to 12, that's a distance of 5. And this height right here is going to be 80, right? So 5 times 80. So that's how we can find the work for this particular example here. So let me just go ahead and write this again. So work is really the area underneath the curve. And the numbers we had were 7 times 140 plus 5 times 80. And when we compute those numbers and add them, we get 1,380 joules of work. Okay, that's it for that particular problem. Now for part B, the question is now saying that after the farmer had pushed the 240 kilogram cart 12 meters, it was moving with the velocity of 2.2 meters per second. And what is the cart's kinetic energy? Okay, let's go ahead and find the kinetic energy here. So we know the mass is equal to 240. And it's moved the distance of 12 meters, and the final speed here is going to be at 2.2 meters per second, and we want to find the cart's kinetic energy. Well, kinetic energy is simply equal to 1/2 mv squared. So here's my 1/2, my mass is 240, and the speed here is 2.2, and we just square that. Okay. And if we compute the numbers there, we get 580.8 joules for the kinetic energy there. Okay, and for the final question here, we have an efficiency question. So what is the efficiency of this process? So we know that efficiency is equal to the work out divided by the work in. Okay, so the work out for this particular example is this right here, so 580.8. So that is the work that was produced. And that's because we're using a final speed here, right? So final speed, we're calculating kinetic energy, and therefore we can, that's going to be the output here, right? And it should just be noticed that when we're talking about work, right, you know, work can also equal to like your kinetic energy using the energy work theorem. And also we need the answer from part A to find the work in here. So from part A, the answer was 1380. And then we just times this by 100, and we get a percentage of 42.29%. Okay, so that's how you can calculate efficiency for this particular graphing question here. All right, let's look at one more graphing problem, and that will conclude this homework video guide. Here's a final graphing question for this video guide. And in this problem, a student plots the graph below showing the kinetic energy of a motorbike versus the square of its velocity v squared. Okay, so we have our kinetic energy over here on the y-axis, and we have just v to the power 2, your I guess your velocity squared on the x-axis there. So we got to figure out what is the slope of this graph here. Okay, so we know that slope is equal to your rise over your run. And if I look at my rise here, I mean the height here is 20,000 joules of energy divided by the run, and my run here is going to be 400. Okay, so a 20,000 divided by 400 is going to be 50. Now, the units are technically, you know, joules on the numerator, and the denominator is meters squared divided by a second squared. So if you want, you can say joules divided by meters squared per second squared. So that's an acceptable answer for the slope. I'll just copy that down over here. So 50 joules divided by meters squared divided by s squared. And then the question asks, what does the slope represent? So we know the magnitude is like 50, but what does this 50 really mean? Okay, since we have kinetic energy on the y-axis, let's just say kinetic energy is equal to the formula 1/2 mass times your speed squared. Okay, if I want to get rid of this 2, I can multiply the left-hand side by 2, so I get 2 times the kinetic energy equals to the mass times, you know, your speed or velocity squared. And then if I divide both sides by the velocity squared, I get mass equals to 2 times on the left-hand side. And I will just write this as kinetic energy divided by v squared. Okay, so don't worry about this 2 here. 2 is just a number there. What I'm more focused about are the units, right? So here's 2 as a number. Now, what are my units for kinetic energy? Well, kinetic energy is measured in joules. And then we have speed or velocity down there, and that's measured in meters per second. But since there's a square here, we got to put a square there and a square there. All right, so I believe these were the units that we had in our previous problem here, joules divided by meters squared divided by s squared, and that's simply equal to the mass. Okay, so what does the slope represent? The slope represents mass. Okay, and that comes from the kinetic energy formula there. Okay, let's go ahead and do the last follow-up question for this particular problem. And if I go to this last follow-up question here, using the axes below, we now want to sketch the graph of kinetic energy versus velocity for this motorbike, and there's no need to plot any data points. Okay, so the only problem for the only variation for this problem now is we just have our velocity down there, and velocity is measured in meters per second. So in the previous case, we had velocity squared, but now we just want to graph the velocity, which is measured in meters per second, and then we just have our kinetic energy over here, right? So kinetic energy, and that's measured in joules. Okay. In order to kind of maybe set this problem, we know from part A, the slope was equal to 50. And from part B, that 50 really meant that we had 50 kilograms, all right? So from parts A and B, we know the mass of this particular object is going to be 50 kilograms. Okay, so what we're going to do now is we're going to set up a little table here. Okay, and what we're going to do is we're going to put our velocity on the x-axis, and let's just go ahead and label this using the same numbers from the original graph. So when we're dealing with velocity, I believe we had numbers like 100, 200, and 300. So let's go ahead and put in 0, then 100, then 200, and then 300. And then let's go ahead and find our kinetic energy. So EK for kinetic energy. Okay, so if I want to find my kinetic energy, we know that's equal to 1/2 times the mass times the speed all squared, right? So in our first case, we have 1/2, and the mass is always going to be a 50. And then we're going to multiply that by our first, our speed or velocity data point, which is going to be 0. So 0 to the power of 2, and that equals to 0. So there's going to be a 0 over here. Okay. Now let's look at what happens when we have a velocity of 100. So if we calculate that, that's going to be 1/2 times 50 times 100 squared. Okay, if we do that, that's a pretty big number here. We get 250,000. So this will be 250,000. And this is measured in joules, right? Okay. Now let's take a look at when our velocity is 200. So if we need to do the math on that, we get 1/2 times 50 times now 200 all squared. And this will give us 1 million, I believe. So 6 zeros. Right, so 1 million. All right, and then finally we just now plug in our speed or velocity of 300 here. So it'll be 1/2 times 50 times 300 all squared, and this gives us another massive number here, over 2,250,000 joules. So 2,250,000 joules. All right, and basically we can just kind of do our best to plot these 4 points, and then we should be finished this particular example. So in the very first case, what's probably easy to graph is the coordinates 0, 0, which is right there. And then we're at 100, I guess we have a kinetic energy of 250,000. So let's label this as 250,000 joules of energy. So we have a dot right there. And then we're at 200, and we're now at 1 million, right? So this will be like 500,000 right here. So millions can be over here, right? This is the 1 million mark. So at 200, we're over there, right? So I can't really plot any more on this graph here, but we kind of get this exponential kind of a graph there. And we'll just say this is 1 million at the top. All right, so that's how you can graph the data for this particular question there. And parts A and B is very important because then you know that the mass of this object is 50. And once you know the mass, you can easily just calculate the kinetic energy for every single velocity point. So 0, 100, 200, and 300. Those are some of the values that we have from part A. So if I go back to my part A graph, I'm just referring to, this is 0, this right here is 100, this is 200, this 300, and that's 400. So you can use kind of those numbers to kind of figure out what's happening for your velocity there. All right, so that concludes this homework help video guide.